Hi everyone, in this video I'm starting a series about Fourier analysis, which is the most important branch in harmonic analysis, and it has a tremendous amount of applications in various areas of science. Now Fourier series is the base for this very large family of transforms that include Fourier transform, discrete time Fourier transform, discrete time Fourier series, short time Fourier transform, and fractional Fourier transform, discrete cosine transform, discrete sine transform, fast Fourier transform, and so on. And it's even important for other Fourier-related transforms like Hilbert transform or Laplace transform or Mellon transform. We'll try to cover all of these in next episodes. Now, before starting with Fourier series, we need to cover this topic, the addition of periodic signals. If we have a periodic signal, let's say a square wave or a sinusoidal or a triangular wave, just any periodic signal that has a frequency of f1 hertz. If we add another periodic signal, just anyone that has a frequency of f2 hertz. Now the results signal, is it periodic or not? And if it's periodic, what's the frequency? Actually, there's no simple answer to this question because actually it depends on whether the ratio f1 over f2 is integer or not. Is it a fraction or integer? So let's just take a numerical example to illustrate the idea. If we have a periodic signal that has a frequency of 1 Hz and another periodic signal with a frequency of 0.8 Hz. Now we are going to add these two signals. So if this is the time axis, so I'm not going to draw the y-axis because I just don't care for the shape of these two signals. So all conclusions I'm going to make are valid for any two periodic signals with these frequencies. And this is the time axis for the second signal. Now, the first signal will have a duration of 1 second. So starting from t equals 0, its first cycle and ends up at t equals 1 second. So this is the first cycle of the first signal. The second one with 0.8 Hz frequency having a duration of 1.25 seconds. So its first cycle starts from t equals 0, ends up at t equals 1.25 seconds. So this is the first cycle of the second signal. Now adding up these two signals, what do we get? Okay, we get a signal that we just don't care for its shape, okay, but we're sure that it will not repeat itself neither at t equals 1 nor at 1.25 seconds. Because this part of the first signal is being added with this part of the first signal for the first time. So the result signal having a new shape over here. So going on with this, the first signal starts the second cycle from t equals 1 and ends up at t equals 2. And the second signal starts from t equals 1.25 ends up at t equals 2.5 seconds. First signal starts its cycle from t equals 2 ends up at t equals 3. And second signal starts from t equals 2.5 ends up at 3.75. First signal starts from t equals 3 ends at t equals 4. This is the fourth cycle, and the fifth cycle ends at t equals 5. While the fourth cycle of the second signal starts from t equals 3.75 ends up at t equals 5. So this is the end of the fourth cycle of the second signal. You can trace what's going on over here to make sure that the result signal is not repeating itself. Why? Because there are points of these two signals that are being added together for the first time, causing new values in the result signal. Now this is happening everywhere over here. For example, this part is added with this part for the first time, and this as well, and so on. Now t equals 5 is a very important moment since both of the signals ended an integer number of cycles at t equals 5, and now they are going to start new cycles after this moment, just like what happened when t equals 0. So what does this mean? This means that all this scenario will start to repeat itself over and over again every 5 seconds, causing the result signal to repeat itself every 5 seconds. So it's all about this critical moment. When will those two signals meet again and start new cycles, just like they did when t equals 0? We can also see that it doesn't matter if this is the fourth cycle, and this is the fifth cycle, or this is the 16th cycle, and this is the second cycle. All it matters is that they are both going to start new cycles from the same moment. And the index of these cycles doesn't matter. So we can say that a 1 Hz periodic signal plus a 0.8 Hz periodic signal gives you a periodic signal having a duration of 5 seconds or 0.2 Hz frequency. You can check these frequencies as well. You can try to add a 1.4 Hz periodic signal plus 1.618 Hz periodic signal you will get a signal of 2 MHz frequency. You can also check that 1.4 Hz periodic signal plus a 1.6 Hz periodic signal, you will get a periodic signal of 0.2 Hz frequency. For this series, we're interested in adding signals with certain type of frequencies, signals that have frequencies multiple of each other. For example, 1 Hz frequency and 100 Hz, 0.4 Hz, and 1.2 Hz, 1.5 plus 3, and so on. Now, for those type of signals, when adding them together, you'll get a signal that has a frequency equals to the lowest frequency. So 1 plus 100, you'll get a signal with 1 Hz frequency, 0.4 plus 1.2, you get a 0.4 Hz, 1.5 plus 3, you get a signal of frequency 1.5 Hz. What's happening is that the low frequency signal is doing a cycle during a capital T second duration, while the highest frequency signal is doing an integer number of cycles within this duration. So when we add those two signals, the resulting signal will have a duration of t seconds. Say this moment is repeating itself when t equals capital T. So for the example we had earlier, that 0.4 plus 1.2, get 0.4, what's happening is that the signal with 0.4 Hz frequency is doing a cycle during 1 over 0.4 second, while the signal with 1.2 Hz frequency is doing 3 cycles during this duration. So when adding these two signals together, we get a signal having a frequency of 0.4 Hz, which equals to the frequency, the lowest one. Similarly, for 1 plus 100 and for 1.5 plus 3, where we can see that 3 Hz is 2 times 1.5 Hz. Now, if one claims that a periodic signal is composed from an infinite number of periodic signals, what's the topic we had earlier imposes? Okay, assume we have a square wave. There's a frequency of 1 Hz. Now, Fourier claims that this signal is composed from infinite number of sinusoidals. Now, what's the nature of frequencies of these sinusoidals? So, if this is 1 Hz, and we are going to add an infinite number of sinusoidals, add up them together to get this signal, we can say that we start with a 1 Hz sinusoidal. If we add a 2 Hz sinusoidal to 1 Hz, we'll get a sinusoidal of 1 Hz as well. Adding 3 Hz to the signal, which appeared to have a frequency of 1 Hz. So 1 Hz plus 3 Hz signal, we get a signal of 1 Hz again. Adding a 4 Hz signal to the signal, which have a 1 Hz frequency, will give us a signal that has a frequency of 1 Hz again. And so on. So we can add 5 Hz, 7 Hz, 6 Hz, 7 Hz, and up to infinity, we will get a signal that has a definitely frequency of 1 Hz only. We had earlier that sum of two signals having a frequencies multiple of each other equals to the lowest one. So if we draw the spectrum of this signal, so this is the frequency, so it has a 1 Hz component, a 2 Hz component, a 3 Hz component. We don't know yet the amplitude of these components. We'll talk about that later. But basically, we're talking about the nature of frequencies, the component that the signal may contain. So 4 Hz, 5 Hz, and so on. So we can basically say that this signal may contain these frequencies. It may not contain them as well. But at least we don't have any issue concerning that the signal contain these frequencies. We can also say that this signal is impossible to contain a component that has a frequency of 1.1 Hz, or 2.5, or even 3.124568. Because if these frequencies are contained in this signal, you wouldn't get a signal that has a frequency of 1 Hz. That means when you add 2.5 to 3 Hz, you would never get a signal that has a frequency of 1 Hz. So these frequencies, if they are contained in this signal, they will corrupt the duration of the signal. It will never be a 1 second. So it may only contain these frequencies that are multiple of this one, the 1 Hz. So if we call this frequency the fundamental frequencies, so all of these are multiple of this one. You can see that the existence of these frequencies will not corrupt the duration of the fundamental frequency, which is 1 Hz. So we have the signal having a duration of 1 second. Sorry, this is 1 second, not 1 hertz. Okay, since this is time axis. So to summarize that, we'll say that this signal, a square wave, that has a duration of 1 second, or a frequency of 1 hertz, let's just call it f of t. So we say f of t can be decomposed of an infinite number of sinusoidals that has these frequencies, sine 2 pi times n times t, and n goes from 0 to infinity. So it takes, when n equals 0, there's no signal. When n equals 1, a fundamental frequency of 1 hertz. When n equals 2 hertz. When n equals 3 hertz, and so on. We also made an argument that this signal may never have a component that has a frequency lies between 1 hertz and 2 hertz. For example, 1.1 or 1.1568 or any other frequency. Why? Because the existence of such frequency will corrupt the duration of the signal. It will never be 1 second, as we can see here. So we can say that these frequencies are not contain this signal. Not even the frequencies lie between 2 and 3. So its spectrum is just a discrete number of frequencies. 1, 2, 3, 4, and so on. So at the end of this topic, the addition of periodic signals, we ended up with this formula. Actually, each component of those having a certain magnitude, okay, let's just call them Bn. Okay, so this is B1, this is B2, this is B3, this is B4, and so on. We'll talk about them later. As for now, we say that this is the nature of frequencies that may be contained in such a periodic signal. Now, to find the magnitude of each component we talked about earlier, we need to talk about the phenomena of orthogonality of sinusoidals. If we multiply a 1 hertz sinusoidal, so sine 2 pi t, we multiply it by a sinusoidal with 2 hertz frequency, so sine 2 pi times 2t, and integrate the result over 1 second, which is the period of the signal. Okay, what's the result? Now I'm not going to solve the problem analytically, instead just show you the result graphically. So we have a 1 hertz sinusoidal, which is the square-styled curve, and 2 hertz sinusoidal, which is the line-styled curve, and the result of multiplication, which is the thick-styled curve. Now I'm going to find the area under the result of multiplication. So we can see that the area is obviously 0, since the result of multiplication is fluctuating around the x-axis. So we can see here that the result of integration is 5.2 times 10 to minus 15, so it's effectively 0. This is due to the usage of numerical integration. Okay, what about 1 hertz multiplied by 3 hertz sinusoidal? We'll see what's going on. So this is 1 hertz, and this is 3 hertz, and this is the result of multiplication. Okay, we'll find the area as well. So I'm going to integrate from 0 to 1. So we can see that the result is effectively 0 as well. So what we had earlier is that the result of this integration is 0. We also had that integration from 0 to 1 to sine, for sine 2 pi times t multiplied by a 3 hertz sinusoidal, sine 2 pi times 3t equals 0 as well. In fact, the result of multiplying this 1 hertz sinusoidal by any other sinusoidal that has a frequency that is multiple of 1 hertz, say n hertz, is 0 as well. You can check that analytically. Unless n equals 1. So if you multiplied the 1 hertz sinusoidal by itself and integrate the result, you wouldn't get a 0. So this is the area is not 0, of course. Actually, the result of integration is 0.5. Now, mathematically, this integral is called correlation between this signal and this. If the result of correlation is 0, those two signals are said to be orthogonal. Now, what about the 2 hertz sinusoidal? Actually, if you try to find the correlation between the 2 hertz, so sine 2 pi times 2t, and 1 hertz, for example, we had this earlier, the result was 0. Okay, if you try to evaluate the correlation between the 2 hertz sinusoidal and 3 hertz, so times 3t, you find it 0 as well. Okay, and for 4 hertz and 5 hertz and 6 hertz, so we can say that integration from 0 to 1 for sine 2 pi times 2t multiplied by sinusoidal of n t dt that has a frequency of n hertz is 0. Now you can prove that analytically or just graphically as we did earlier. Okay, so we say that 2 hertz is orthogonal to 1 hertz, 3 hertz, 4 hertz, 5 hertz, and all the frequencies unless n equals 2. So of course it's not orthogonal to itself, that's impossible. Okay, now to summarize this, we say that 1 hertz is orthogonal to 2 hertz, 3 hertz, 4 hertz, 5 hertz. They appear to be orthogonal to all those frequencies, and so on. And the 2 hertz appear to be orthogonal to 1, to 3, sorry, not 2. It's orthogonal to 1 hertz, 3 hertz, 4 hertz, 5 hertz, and so on. So as the 3 hertz, it's orthogonal to all other frequency. So we can write this generalized formula, the integration over time, a single period, of sine 2 pi times nt multiplied by sine 2 pi mt dd equals to 0 if n is not equal to m, and 0.5 if n equals to m, where one of those n or m is an integer multiple of the other one. So if n is 1 hertz, m is 1 hertz as well, you get the result is 0.5 as we had earlier over here. If n is equals to 2 hertz and m equals to 2 hertz as well, you get 0.5 also. So every time n equals to m, the result of integration is 0.5. We say that any frequency is not orthogonal to itself since the result of correlation is not 0 when n equals to m. So for this example, if n equals to 2, the result of this integration is 0.5. Back to our decomposition, we assumed earlier that our function, the square wave of t, can be decomposed into a sum of infinite number of sinusoidals, sine 2 pi times nt. And we were intending to find the magnitude of each component. So let's expand this summation. If you put n equals 0, you won't get a signal. So starting with b1 sine 2 pi t plus b2 sine 2 pi times 2t plus b3 sine 2 pi times 3d, and so on. Okay, now we need to find b1, b2, b3, b4, and so on. And let's just start with b1. How to find b1? To find b1, we multiply the signal f of t by the sinusoidal to find its magnitude. So f of t times sine 2 pi t. This is f of t, our original signal, the square wave. Okay, this is one cycle of the signal. And integrate the result over one period of the signal. Okay, let's just imagine what's happening. We were integrating f of t multiplied by sine 2 pi t, a 1 hertz sinusoidal, of a single period of f of t, which is 1 second. We earlier assumed that f of t is the sum of infinite number of sinusoidals. So b1 sine 2 pi t plus b2 sine 2 pi times 2t plus b3 sine 2 pi times 3t plus sine b4 sine 2 pi times 4t, and so on. So this sinusoidal we multiplied by f of t will be distributed over all this sum. This integration operator will be distributed as well over this sum. However, we said earlier that the correlation between a 1 hertz sinusoidal and a 4 hertz sinusoidal is 0, while being integrated from 0 to 1. And it's 0 as well while when you integrate the multiplication of a 1 hertz and 3 hertz, a 1 hertz and a 2 hertz, and all up to infinity, 4 hertz, 5 hertz, and so on. Except when you multiply a 1 hertz sinusoidal by a 1 hertz sinusoidal as well, you get a value. So if you multiply this 1 hertz multiplied by 1 hertz, so you get this area when you integrate from 0 to 1. So we can say that the result of this integration is produced by the interaction between this sinusoidal and this very same component that is contained inside f of t. So we can say that all these sinusoidals didn't make any contribution to the result of this integration, because the result of correlation between this frequency and all these frequencies is 0. The only effective frequency is the component that is similar to the sinusoidal we multiplied the f of t by, which is 1 hertz. So only the 1 hertz component inside f of t had a contribution to the result of this integration. So if this is the sinusoidal we multiplied by, this is the 1 Hertz, and this one is the 1 Hertz component inside f of t. So it has a magnitude of b1. So here we have b1. And the result of this integration was this area. We also need to say that the magnitudes of these components, b2, b3, b4, and so on, doesn't affect the result of integration. For example, if the correlation between a 1 Hertz and a 2 Hertz sinusoidal is 0, even if these two sinusoidals have a magnitude that's 5 or 6 or just any other magnitude. Okay, so since these magnitudes will be just a constant coefficient for this integral, for example, here we have 30. 30 times 0 is 0. For example, we said earlier that the 1 Hertz sinusoidal, so this is 1 second, this is time axis, and the 2 Hertz sinusoidal are orthogonal to each other. So the result of multiplying these two signals gives you this. Okay, now the area under this signal is 0 regardless of the magnitude of this one or this one. So if you multiply this signal by a factor, say 5, you get this. Now the result remains 0. Okay, now to summarize, we said that the result of integration for f of t multiplied by sine 2 pi t, a 1 Hertz sinusoidal, integrated over a single period of f of t, the result of this integration is obtained by the interaction between this sinusoidal, we multiply f of t by, and this very same frequency component that is contained inside f of t, which is 1 Hertz. Let's evaluate this integration. We have f of t is 1 from 0 to 0.5 and minus 1 from 0.5 to 1. So we have integration from 0 to 0.5 for 1, f of t equals 1 in this period. So 1 times sine 2 pi t dt plus integration from 0.5 to 1, where f of t equals to minus 1 in this part of the signal. So minus 1 multiplied by sine 2 pi t dt. So we can say that f of t equals to plus 1 when t is larger than 0, less than 0.5, and equals to minus 1 when t is larger than 0.5 and less than 1. This is the definition of f of t during a single period only. So when you evaluate this integral, you'll find out that the result of this integration is 2 over pi. Now, what's the meaning of the result of this integration? So we obtained that f of t times sine 2 pi t equals to 2 over pi. Actually, the result of this integration is directly proportional to the magnitude of the 1 Hertz component that is contained inside f of t. So we can prove that as follows. When we assumed that f of t is b1 sine 2 pi t plus b2 sine 4 pi t plus b3 sine 6 pi t and so on. We also proved that those components are orthogonal to the 1 Hertz. Only the 1 Hertz component is not orthogonal to itself, of course. So we can see that b1 is directly proportional to the result of integration. For example, we can illustrate this graphically. This is the 1 Hertz that we're multiplying f of t by. And this is the 1 Hertz component inside f of t that has a magnitude of b1. We are trying to find its value. So this has a magnitude of b1. If you multiply those two signals, then you get an area that is directly proportional to b1 value. So we can rewrite this integration as follows. F of t times sine 2 pi t dt equals to integration from 0 to 1 for b1 sine 2 pi t. Now what's this? This is the 1 Hertz component inside f of t, since all other components are orthogonal. And this is the sine 2 pi t dt, which equals to b1 outside the integration sine 2 pi t times sine 2 pi t dt. We earlier found that the result of integration is 2 over pi. We have earlier found that the result of correlation between 1 Hertz and 1 Hertz, this is called autocorrelation, appeared to be 0.5. So now we can find b1. So we found the result of this integration appeared to be 2 over pi when we evaluated it earlier, And we also found that the result of this integration is obtained only by interaction between this term and this component from f of t. We also found that autocorrelation of 1 Hz appeared to be 0.5. So this means that B1 is 4 over pi. So this is the magnitude of the 1 Hz component inside f of t. You can understand it as follows. Now, if the magnitude of the 1 Hz component inside f of t was 1, that means B1 equals to 1, we'd find the result of integration appeared to be 0.5. However, we found it appeared to be 2 over pi. This means that B1 equals to 4 over pi. So similarly for the 2 Hz component. So if f of t equals to B1 sine 2 pi t plus B2 sine 4 pi t, the 2 Hz component, plus B3 sine 6 pi t, the 3 Hz component, and so on. And we intend to find B2. What do? We multiply f of t by a 2 Hz component, by a 2 Hz sinusoidal actually, sine 4 pi t. What would happen? This sinusoidal would be distributed for all these terms. And we also found earlier that the 4 Hz component is orthogonal to all other frequencies except itself. You find the result of this integration from 0 to 1. You get a value. We also found that the result of integrating a 2 Hz sinusoidal multiplied by itself gives you 0.5. However, we got this. This means that the magnitude of the 2 Hz component inside f of t is this value divided by 0.5. So to generalize the idea, we say when f of t equals to summation bn sine 2 pi times nt from n equals 0 to infinity, to find bn, you need to find this integration from 0 to 1, which is the period of f of t, for f of t times sine 2 pi nt. When you find the first component, the fundamental harmonic, put n equals 1, and so on, dt. And when you find the result of this integration, divide the result by 0.5. So this is a formula to find the component, to find each component of sinusoidals that are contained in f of t. Now, in context of transforms, we say that this is a forward transform. This is an inverse transform. When you use this formula, you have transformed f of t into the frequency domain. So we write, this is a frequency, fundamental frequency of 1 Hz. You find its component, B1. The second harmonic has a magnitude of B2, and so on. So f of t is being analyzed into the frequency domain. So this is called an analyzed transform. It does analyzing the signal, while this is called synthesizing transform, since it sums up all these components back to time domain. So we can say that this is forward transform to frequency domain, and this is inverse transform to time domain. Now let's try another signal that is an even signal, say this, where f of minus t equals to f of plus t, which means this is an even signal, unlike the last signal we analyzed, which was odd signal, since f of minus t equals to minus f of plus t. Now if you try to analyze this signal into sinusoidals, so f of t equals to summation n equals 0 to infinity for bn sine 2 pi n t, and now you try to find bn, you will find out that all of them are 0, regardless of n value. So what does that mean? If all these bn's are 0, this means that f of t equals 0. Actually, the triangular even function doesn't have any sinusoidal component. Instead, it has cosinusoid components. So when you say f of t, we mean the triangular even function equals to summation from n equals 0 to infinity for an times cosine 2 pi nt. It has a cosinusoid components. An can be found similarly by 1 over 0.5 integrating from 0 to 1 or f of t times cosine 2 pi nt dt. So we need here to specify the duration of the signal, because this formula is not evaluated for any triangular wave, only for this one that has a duration of 1 second, just like the triangular wave. So this formula is written for this wave, has a duration of 1 second. Here the magnitude is not very important, any magnitude is okay. Now to generalize the idea that can be used for any periodic functions of a 1 second duration that is not even nor odd, say like this periodic function. Okay, it's not even and not odd as well. So if we have this f of t, we say it has sinusoid and cosinusoid components at the same time. So we say a n cosine 2 pi nt plus b n sine 2 pi nt, if this is 1 second. So for odd signals, this part is 0. For even signals, this part is 0. For general signals, both parts exist, where an equals to 1 over 0.5 integration from 0 to 1, since it had a 1 second duration, f of t times cosine 2 pi nt dt, and bn equals to 1 over 0.5 integration from 0 to 1 f of t multiplied by sine 2 pi nt dt. I also need to say here that you don't need to worry about the interaction between sinusoid and cosinusoids within the signal. So we assumed as generalization that f of t, which is a periodic function that has a duration of 1 second, equals to a naught cosine 2 pi times 0t plus a1 times cosine 2 pi times 1t plus a2 cosine 2 pi times 2t and so on, plus b naught times sine 2 pi times 0t plus b1, the coefficient of the second sinusoidal component, sine 2 pi times 1t plus b2 sine 2 pi times 2t and so on. Now when you need to find a1, for example, what do? So you find a1 equals to 1 over 0.5 integration from 0 to 1 for f of t times cosine 2 pi t, a 1 hertz component, dt. Now, since we assume that f of t equals to this sum, this means that this cosinusoid will be distributed on all this sum. We have the correlation between a 1 hertz component, so cosine 2 pi t, and other cosinusoids that has a frequency, say nt, where n is an integer multiple of 1. Since this cosinusoid has a frequency of 1 hertz dt, the result is always 0 unless n equals 1. We get a result of 0.5. Now, to understand the interaction between these cosinusoids and sinusoids components inside f of t, we need to see this. If we multiply a 1 hertz sinusoid by a 1 hertz cosinusoid, what do we get? So this is a 1 hertz cosinusoid. Okay, so this is 1 second. We multiply them together. What do we get? A positive quantity times a positive quantity would be positive. Negative times positive would be negative. And negative times negative would be positive. And then negative. So when we integrate this signal over 1 second duration, we get 0 as well. So we can say that integration from 0 to 1 for sine 2 pi t times cosine 2 pi t dt equals 0. So to generalize, we say that the correlation between a 1 hertz cosinusoid and an n hertz sinusoid is always 0, regardless of value of n. Of course, it needs to be integer. And of course, the same thing for the sinusoids. So we have integration. For example, for a 1 hertz sinusoid, okay, it's orthogonal to all other cosinusoids, regardless of their frequency. So to summarize, we say that the 1 hertz cosinusoid component is not only orthogonal to all other cosinusoid components, but it's also orthogonal to all other sinusoid components, even to the same 1 hertz sinusoid component. Same thing can be said about any other component. For example, this 2 hertz sinusoid component. It's orthogonal to all other sinusoid component and cosinusoid component as well. It's only not orthogonal to itself, but it's also orthogonal to a 2 hertz component but a cosinusoid signal. So you don't need to worry about the interaction that will happen when you find the value of this integration. When you multiply by a certain frequency, that is sinusoid or cosinusoid, it will be interacted with this very same component inside f of t, whether it was a sinusoid or a cosinusoid, and it will be orthogonal to all other components of the both types. So we can summarize the idea with these formulas. We showed that the integration of sine 2 pi times nt multiplied by sine 2 pi mt dt is always 0 unless n equals m. Result appeared to be 0.5. Also, the integration from 0 to 1 for cosine 2 pi times nt multiplied by cosine 2 pi times mt dt equals to 0 unless m equals n. The result of integration will be 0.5. And finally, we showed that the integration of a single period of sine 2 pi nt multiplied by cosine 2 pi mt dt is always 0, even if m equals to n. That means that a 1 Hertz sinusoidal is not only orthogonal to all other sinusoidal frequencies except itself, of course, but it's also orthogonal to all other cosinusoidal frequencies. That's why the energy consumption in the capacitor coil is 0, because there's a 90-degree shift between current and voltage. So if this is the current and this is voltage, or this is voltage and this is current, depends on when you're dealing with a capacitor or a coil. So the product of voltage and current is power, and the integration of power over time is energy, which equals to 0, so there's no energy consumption. Now the final generalization, all what we had earlier was valid for a 1 Hertz periodic function. We need now to find formulas for periodic function with any duration. So say we have f of t that has a duration of 1 second. Let's say t seconds. Okay, so it has a frequency, f equals 1 over t. Let's call it f naught. Now we analyze the signal as follows. We assume that f of t equals to an infinite sum of sinusoidals that are multiples of f naught. So 2 pi times n f naught t multiplied by bn plus an cosine 2 pi times n f naught t. So when n equals 1, we have a fundamental frequency that has a frequency of f naught, and then multiples of f naught, 2f naught, 3f naught, 4f naught, and so on. So its spectrum will be as follows. Let the spectrum be the includes the magnitudes of the sinusoidal components only, and another one that includes the magnitude of cosinusoidal components. So if this is the frequency axis, we have an and bn. Okay, so it has f naught hertz fundamental component, 2f naught, 3f naught, and so on. So it also have a discrete spectrum. It doesn't have any other frequencies between those two frequencies, for example. It only have those discrete number of frequencies, as we showed earlier. Now the formulas for an and bn are similar. So an equals to 2 over time integration of a single period for f of t times cosine 2 pi n f naught t dt, and bn is defined by 2 over t integration of a single period f of t sine 2 pi n f naught t dt. Integration can be from 0 to capital T or from minus t over 2 to plus t over 2. In all cases, it will cover a single period. Now, similarly, when you multiply this function by a nf naught sinusoidal, it will be orthogonal to all other components inside f of t, except the component that is contained its same frequency. And the result of integration will be due to this effect. However, if you assume that the magnitude of the nf naught component inside f of t is 1, and you evaluated this integral, so you get integration from minus t over 2 to plus t over 2 for sine 2 pi nf naught t. So you assume that its magnitude is 1 and multiplied it by your sinusoidal, which is sine 2 pi nf naught t dt. You will get a result of t over 2. Check this result by yourself analytically. So if the magnitude of this component was 1, you would get a result of integration of t over 2. However, if you got this, you need to divide it by t over 2 to get the real magnitude of that component. So dividing by t over 2 or multiplying by 2 over t. So that's why you see this component over here. It's for normalization purposes. Now the same thing applies for an, with an exception where n equals 0, the normalization factor will be 1 over t, not 2 over t. You can check that by yourself. So I'm finishing this by writing down the formulas of the orthogonality between sinusoidals and cosinusoids. So we can see here that the correlation between sinusoid and cosinusoid is always 0, even if the frequencies are equal, even if n equals to m. And the orthogonality between sinusoidals, they're always orthogonal, except when n equals m, that is, a sinusoidal is not orthogonal with itself, of course. Same thing applies for cosinusoids. These formulas, which our Fourier series is based on. So finally, the formula of Fourier series, f of t equals to summation from n equals 0 to infinity, an cosine 2 pi nf naught t, plus bn sine 2 pi nf naught t, an equals to 2 over t integral from 0 to t f of t times cosine 2 pi nf naught t, and bn equals to 2 over t integral over time f of t times sine 2 pi nf naught t dt. Except when n equals 0, so this is for n doesn't equal 0, for n equals 0, a naught equals to 1 over time, integration over time f of t dt.